Last lecture we discussed about Ampere's law for magnetostatics. And we know that for electrostatics, we mainly want to find out the electric field. So what we know is the electric field is really correlates in some sense, del cross this E equals to 0. And then we also have this Gaussian's law is really to figure out the divergence of this electric field is equals to rho divided by epsilon 0. And if we write it down in the integral format, we can define an area. Okay, we calculate the surface integral, and we will find this is the amount of charge that are included in this Gaussian surface, and then divided by epsilon 0. Okay, so this is what we have for electrostatics. And for this magnetostatics, we mainly need to calculate the magnetic field. And we know that the magnetic field is divergenceness. In other words, that del dot B equals to 0. And we also have this Ampere's law. Is del cross B equals to this mu 0 times J. Okay, if we write it down in this integral format, we define a Amperian loop. Okay, we do the line integral, okay, around that loop, and then this is equals to mu 0 times the amount of current that are included inside that loop. Okay, so you can see that they are pretty symmetric, okay, for electrostatics and magnetostatics. And what you can see that this one tells us, okay, so this is 2, this is 2. So this Gauss's law tells us the electric field is really diverges away from a positive charge, and the electric field lines originate on positive charges and then terminate on the negative charges. Okay, while the magnetic field, okay, del dot B is equals to 0. Really, we know that the magnetic field course around a current. Okay, so in other words, these magnetic field lines don't begin or end anywhere. Okay, because if magnetic field lines also like electric field lines, they must originate from somewhere and then terminate on the other things. Okay, because if we need to do that, that means the magnetic field, the divergence will be non-zero. Okay, so the magnetic field often form this closed loop, or extend out to infinity. Okay, so in other words, that not like electric field lines. Okay, magnetic field lines, they just course around. Okay, so in other words, there are no point sources for the magnetic field. Okay, so this is very important. There are no point sources for the magnetic field, not like the electric field. We have positive charge, we have negative charge. So B is thus divergenceless. Okay, so there are no magnetic charges. Sometimes we use the word magnetic monopoles. Okay. Okay, so this is looking at these formulas, that is what we know. Okay, so electric forces are often much larger than the magnetic forces. So this is mainly due to the size of this, one is the electric field is proportional to 1 over epsilon 0, while the magnetic field is proportional to mu 0. Okay, so epsilon 0, is 8.85 times 10 to minus 12. Okay, so this is the unit of Coulomb Newton meter square. And this mu 0 is equals to 4 pi times 10 to minus 7. Okay, Newton MP square. And you can see that because this is proportional, 1 over this epsilon 0. So the value, for the electric field is often much bigger than the magnetic field. Okay. So this is just wanted to let you know. Okay. Now I wanted to show you a few examples, to show you how to use this Ampere's law, okay, to find the magnetic field for some simple cases, just like I showed a few examples before for the Gaussian's law, how to figure out the electric field, okay, for some simple configurations, okay. And then later you will see that, this Ampere's law is always correct, but sometimes it's not that useful. We also have to rely a lot of symmetries, okay, in order to figure out the problem. If there are no such symmetries, for the problems we wanted to solve, then it's often difficult to apply the Ampere's law, okay. So now let us consider this one. We have one example. Okay, so let us consider a surface, okay, which is XYZ here, okay, and then we say that this XY plane, okay, is a infinite uniform, a infinite plane, okay, on the XY plane, and we assume there is a uniform surface current, okay, that are moving, along the z x direction. Okay, so the surface current is really k, the magnitude. It is along the x direction. Okay, so we wanted to figure out, what is the electric field, for example, that is some distance away from the xy plane. Okay, so the way to do it, we first, in principle, we can use this Biot-Savart law and do this integral, okay. And here, of course, this problem has quite some symmetries, that we can use. Is infinite, is is just on the xy plane, okay. So it can be shown that the magnetic field can only have a y component, okay. So the way to see that there shouldn't be x component, because the magnetic field should be perpendicular to the surface current, and the surface current is along x direction, so the bx should be 0, okay. And then you can also see that bz should be 0, okay. So the reason, we can just think about it this way. Let us assume that bz is not 0, okay. Let us assume it is a point away from the plane, okay. If it's non-zero, okay, the bz is really positive, okay, for z greater than 0, is negative for z less than 0, okay. So now let us assume we just reversing the direction of the current, okay. So in other words, that if we do that, okay, changing the sign of the current, of course switch the sign of the field. So then we expect that the current will be reversed, and then the sign will change. So that really means the z component, okay, will pointing toward this plane. But we know that because of all the symmetry reasons that are shown here, the z component of this b, okay, uh, shouldn't depend on the direction of the current in the xy plane. So in other words, that we only have this by component that is non-zero. Okay, so then in order to figure out that, so that means there is only by is not zero. So what we can do is we can define an ambient loop. Okay, that is that is straddle on the surface. Okay, and assume it has it is a very small area that are very close to the surface. So what we have this b dot dl, for example, and we know that because of the right hand rule, we know that on the top it should pointing to the left, and on the below the surface it should point to the right. Okay, so what do we really have? If we integral this way and integral this way, if we assume the length is L, so we really just have 2 times BL. Okay, this width we can make it very small and close to 0. Okay, so this one, if we use Ampere's law, we know that it is equals to mu 0 times the current that are included inside this Amperean loop. So this one is really mu 0 times k times this L. So what do you find that is really, you can see that the B field, the value is really mu 0 k divided by 2. Okay, so that is the magnetic field amplitude. And as we said that if it's greater than 0, it should be pointing k should pointing to the negative y direction. Okay, pointing to the left. This is z greater than 0, should be mu 0 k pointing to the y direction when z is less than 0, because it's pointing to the right. Okay, and you can also see here the magnetic field actually is independent of the distance from the plane. Okay, just like what we calculated before for the electric field of a uniform surface charge. So in other words, for a uniform surface charge or uniform surface current, the electric field or the magnetic field is independent of the distance from the plane. So here we are talking about a very long solenoid, which is made of a very long cylinder. Okay, that is has a radius is r, so diameter is 2r. Okay, so there are many wires, okay, that are carry currents, that we widening these wires around this wire. Okay, and we want this so this is the number of these turns per unit length. Let us assume is m. Okay, so here we assume that the windings are very close to each other, so that we can just pretend that each turn is really a circle. Okay, so you don't worry about this small distance along this z direction. Okay, move from the bottom of the circle to the top of the circle. Okay, so in some sense, you can kind of treat this really has a surface current. The K is really each one assume there is a wire. Okay, let us say is I. Okay, So because they are very let us say yeah, this direction, and let us assume, as I said, the number of turns per unit length is n. Okay, so because is these wires, they are very close to each other, you can kind of assume treat it as a surface current that is really n times I. Okay, so now we want to figure out what is the magnetic field here, at any point here. So first, of course, we wanted to figure out the direction of this magnetic field. So, can it have a radial component? Be, if we let us consider, of course, here is a cylindrical coordinate system will be better. So does it have a radial component? So the answer is no. So the reason is for this, let us say if there is a radial component, BS, okay, we use BS. If it's a positive, okay, now we can also do the same trick that I showed previously. Let us assume we revert the direction of the current. So in that case, the BS should then be negative. But just switching the current is physically equivalent to turning the solenoid upside down. And that certainly shouldn't alter the radial components. Okay, in other words, that BS has to be 0. Okay, now how about the phi component? Whether it's B phi should be 0 or not. Okay, so B phi should also be 0. Okay, so the reason to do that is you can kind of define also a Ampere's loop. Okay, that is concentric with the solenoid, and then if you do this B dot dl, which is really this B phi value times 2 pi times the distance, okay, let us say is s, okay, away from the wire, okay, and then this of course equals to mu I enclosed, okay, and because here the current, you see that is really a circular one, okay, the one that included inside this loop is actually equals to 0, so you have to be careful about that, okay, because this loop, this loop that is defined here encloses no current there, okay, so in other words that we can also get B phi that equals to 0, okay, so now let us move this to a little bit far away. Okay, so this is the what we have. The BS should be 0, B phi equals to 0. So then, of course, what we really wanted to have is really equals to the Z component. So BZ must, is not 0. Okay, so then how to figure out this value? Okay, so let us define a loop. Okay, outside first. Okay, so let us assume this distance is A away from here, and this distance, okay, is B away from here. Okay, so let us consider this loop. Okay, so this length is L, and we can make this distance, this width to be very small. Okay, so now if we do this B dot dl, okay, what we really have is really the value that are calculated at A, at this value A, okay, minus let us say the value calculated at B, okay, times L. Okay, we can just consider this loop. Let us consider this direction, okay, to do the integral. Okay, so that is what we have, and as we said, this should be mu 0 times the amount of current enclosed inside this loop, and and this loop is outside the solenoid. So this should equals to 0. Okay. From here, what we have is really we found that BA is equals to BB. Okay. So in other words, that the field that is outside doesn't depend on the distance from this axis, the central axis here. Okay. Okay. And we know that if this distance is goes to infinity, okay, so the b when this distance goes to infinity should equals to 0. Okay, and we know that the distance the b field value doesn't depend on distance, so that really means b should equals to 0 everywhere. This is of course for the case that is outside of this solenoid. Okay, so you can see the argument. From here we get that the outside of this solenoid, the B field value shouldn't depend on the distance. And from here we know that when the distance goes to infinity, it should be 0. And combine these two, we know that the B field value should equals to 0. Okay, just outside the solenoid. Okay, so then how about the inside? Okay, to do inside, what we do is we define also a loop. Okay, that is just a straddle also between cross this surface. Okay, so that half that are inside and half are outside. Okay, so what we do is we also calculated this line integral here. Okay, so what we have is outside. Okay, so let us define a direction. Okay, let us define this way. Okay, so we can also make this width to be very small. Okay, infinitesimally small, so it doesn't have contribution. So then it only have the distance. Okay, inside is, let us assume is b times the length, let us also assume is L. Okay, and then we need to consider the contribution b dot dl here, and there is 0. Okay, because it is outside, and here we showed that b should equals to 0. Okay, so this should be really times mu 0 times k times L. Okay, so this is just the amount of current that are included, okay, inside this loop. Okay, so here you see that there are really current that are enter this loop. Okay, so from here we can see that this one is really mu 0 times k, we said is ni, this is L. Okay, from here we can see that the b should be equals to mu 0 ni. Okay, and we said this b should just have the z component. Okay, so in other words, that b should be mu 0 times ni. So this is really just for, this is inside the solenoid. Okay, in other words, we can summarize it. So if it's inside, so it equals to this. So this is inside the solenoid. Okay, it should be 0 if it's outside the solenoid. Okay, and you can also see from here that if it's inside, it's just pointing along the axis of this solenoid. Okay, the center of the cylinder. Okay, axis of the cylinder. And you also find that this value is a constant. Mu 0 is constant, n is a constant, I is also constant. And you can see that inside this solenoid, the magnetic field is uniform. it doesn't depend on the distance from the axis. Okay. And you can see that we can also increase this n, which is the number of turns per unit length. We can in principle increase this n to increase the magnetic field. So in some sense, here is really a simple device that we can use to produce strong uniform magnetic field. Okay. And even these days, we wanted to generate a strong magnetic field. We try to increase the number of turns per unit length, or increase the current that are flow through each wire, okay, to get a uniform magnetic field. Okay, so that is also what we can do. Okay, so the book also have another example, talking about how to calculate the magnetic field of a toroid. Okay, so I will not discuss it here. If you want, you can take a look to get a better understanding of this. Okay, so here I basically just showed you two examples how to use the Ampere's law to figure out the magnetic field distribution, for some configurations. As I mentioned earlier, like this Gaussian's law, it also relies on symmetries, so that it will be easier for you to calculate, this line integral. Okay, this of course often works, for symmetries like we have infinite straight lines, we have infinite planes, infinite solenoids, or some toroids. Okay, that have very well-defined symmetries. Okay, and we can use we can quickly figure out the direction of the magnetic field, so that it will be easier for us to calculate this line integral, and thus we can use the Ampere's law, in the integral format. Okay, but in many situations, if we don't have such symmetries, we cannot really use it. Okay, now I wanted to discuss a different topic called magnetic vector potential. Okay, so this one, before I talk about this, I just wanted to remind you, when we talk about the vector analysis, we said for any function of a scalar function of phi, the core of is the gradient is always 0. Okay, no matter what is a phi function, del cross del phi should always equals to 0. And we also showed that for any vector A, okay, so if we find the divergence of the core of this vector A should also equals to 0. Okay, so this is what we have, from the vector analysis. Okay, so it works for any function of phi, and here it works for any vector A. Okay, so this is very general. Okay, now let us remember that for the magnetic field, we said the magnetic field really diverges out from positive charges, so it's coreless. Okay, so in other words, we have this. Okay, so if you look at this formula, okay, you can see that we can write down this E as some some gradient of a function. Okay, so that is what we did. We define E as some gradient of a function. Okay, we just negative is just a convention. Okay, So basically, that is u I defined here is -5 here. If you really just directly compare with this one. Okay, and see, so this is V. I should really say V. So this is really a scalar potential. Okay, also we also call the electric potential. Okay, so that is what we did for this. Okay, now for the magnetic field, and we said that the magnetic field is really a divergenceless. Okay, because we don't see the magnetic monopoles, so there are no magnetic charges, like electric charge. So the divergence is equals to 0. So now you can look at this, because any the divergence for any core of a vector is equals to 0. So you can see that we can try to write the magnetic field as the core of a function A, of a vector A. And this vector A, you can see that is similar to the scalar potential that we have for the electromagnetic field. And here we call it a vector potential. Okay, so you can see that how how we can, look by looking this formula, see that we can define a vector potential to do that. Okay, so now we have this, and now we try to figure out how to calculate this vector potential. Okay, so now the only function that we left is this Ampere's law, which says del cross B is equals to mu 0 J. Okay, so now we just plug in. So B is del cross A. Okay, and we can use the vector identities. Okay, you can see from Griffin's book, the second page. Okay, so there we said that this can be written as this. Okay, so in other words, that the Ampere's law, now becomes this. Okay, so now if we have some, density current, volume current density, and J. So in principle, we can solve this equation, and we can figure out A. Okay, and of course, this equation is pretty complicated. Okay, so it's often difficult to figure out this what is the vector potential given a current density J. Okay. So now, we want to simplify this equation so that it will be easier, to calculate, and we can use, all the skills that we learned so far. Okay, so the way to do that is we have to realize that for the potential like that, the electric potential, we have this V. Okay, so in principle we can add a lot of function. Let us say my new V is another V. Okay, plus any function. Okay, any function, I will say any function, okay, whose gradient is 0. Okay, let us say I could for example, we can put a constant there. Okay, of course, del cross this you can see that so the E, because it's minus the del of V. Okay, so if this V now become now V is just if we change it by a constant. Okay, if we do the derivative, it shouldn't change. Okay, so in other words, that this electrical potential has some freedoms. Okay, we can define a value but then we add any constants on, for every point, okay, the value. It shouldn't really change, the physical quantity, the electric field that we wanted to measure. Okay, so this is something very important. And this is for electric field. This is really, where you choose the reference point. Okay, of course, we choose the infinity point, the potential to be 0, but you can change it to any value like 10 or minus 10. The overall electrical field distribution shouldn't change. Okay, and in principle that is the same thing here. If we add this a prime, okay, we originally have the vector potential a. If we give it any function, okay, whose core vanishes, okay, so in that case, because b is really del cross a, okay, so now if you think that this a is my original a plus something where the core vanishes, okay, del cross that new function, and that function has a core that is 0. So in this case, b cross a prime is still equals to del cross a. Okay, so that means the magnetic field is still the same. Okay, so in other words that we want to use this freedom. Okay, so we can, so that means a, we can find one solution for a. Okay, then we also added any function whose core vanishes. Okay, then we still get the same magnetic field. Okay, so in other words, as I said, we have this freedom to add any functions whose core vanishes, to this vector potential. So what we wanted to do is, so that a has some freedom. Okay, so we want to make del cross dot a to be 0. Okay, we have many choices of a we can do. Okay, we want to make the case choose this a so that its divergence is 0. Okay, the reason we do that, you can see that if we make a divergence equals to 0, then this one will just it just becomes 0. So our equation is greatly simplified. Okay, I said the reason is we can have some freedom to choose this a. Okay, so that it becomes 0. Okay, so the reason, so how do we do this? Okay, so what we can see that we, let us say I have my original a, I call it a0. Okay, so this is my original a. My new a, let us say I put it as a function lambda. I introduce a function lambda, and I put it as gradient. Okay, the reason is really, del cross a now is really del cross a0 plus del lambda, and this is del cross a0 plus del cross del lambda. Okay, and we said that for any function, okay, the scalar function, the core of its gradient is really 0. So this one is 0. Okay, so that really means del cross a is really equals to del cross a0. Okay, so in other words that this a and a0, okay, will give us the same magnetic field. Okay, because b is just b cross a. Okay, and both of them will give me, they are equal to each other, give me the same magnetic field. Okay. Okay. So now we said that we want to simplify it to make a del dot A equals to 0. Okay. So del dot A now is del dot A 0 plus del dot del lambda. Okay, equals to 0. Okay, which is really this del dot A 0 plus del square lambda equals to 0. Okay, so we can choose del lambda square is equals minus del dot A 0. Okay, okay. So in other words, that if we find a 0, okay, that satisfies this, okay, we can add it by another gradient of this lambda function, and this lambda function satisfies this equation, and with that this gradient added to this a0, and we have this del, the new a becomes divergenceless. Okay, that will simplify our equations. And you can see from here, what is this? This is really just like a Poisson equation, right? That we learned before. Like the electric field case is minus rho divided by epsilon 0. Okay, so this is a Poisson equation. If we have some charge distribution, how we find the magnetic electric potential. So this function is the same. You kind of just treated this as some charge, you treat it as some potential, and then you can really solve this equation, to figure out this lambda function. Okay, so we know that for this we know that to find this v, what we have, if it's some charge 4 pi 0, and this is rho d tau divided by the cursive r. Okay, so this one, so this of course, if rho goes to 0 at infinity. Okay, so in other words, that we have charges that are contained in some regions, not extend to infinity. Okay, so this is we showed before. Okay, so this is basically, you have some charge distributions, and we want to figure out what is the electrical field that is at some point. Okay, this is just to use this equation. So now if you look at this and this, okay, so they are very similar, and you can see that the basically is really lambda is really just 1 over 4 pi. Okay, because this one has epsilon 0 here, and now you can think about that epsilon 0 is 1. Okay, so now it's just 1 over 4 pi, and rho in this case is just del dot a 0. Okay, okay, so in other words, that we can just use by this analogy help us to figure out what is the function lambda will look like. Okay, okay, so now, okay, so it is actually very important to know that we have this b equals to del cross a. Okay, so in other words, that this only tells us, for a function of a, what it is core should look like. It should equals to b. But this relation doesn't say anything about the divergence of this vector a. So in fact, we have the freedom to pick up whatever del cross del dot a we want to have. Okay, And of course, we like to choose 0. Okay, we can choose 10, 20, whatever number we like. Okay, but 0 is often the simplest choice. So in other words, that you know it is always possible to make the vector potential divergenceless. Okay, so it's always, we can always find another function lambda. Okay, that will add add to the solution that we had before, a0. Okay, it takes a divergence, a gradient, and then add to the original vector a, and make it a new vector a, and then this new vector will have the divergence that equals to 0. So now, as I said, once we have the divergence equals to 0, then the equation that I showed here is just del square a equals to minus mu 0 j. Okay, it's just simplified to this. Okay, so this is is basically still Ampere's law, but is now I use the vector potential instead of the magnetic field. Okay. Okay, and as I said, we know how to solve this equation. So this is basically the Poisson's equation. So if this j goes to 0 at infinity, okay, at infinity, okay, in other words, that the current is also the currents that we have for the problem we wanted to solve, they are also contained in some area, okay, some volume. Okay, so if j goes to infinity, as I said, this is just a Poisson equation, and is very similar to this equation where we have for the electric potential. Okay, so we can just directly write down this equation. The solution to this equation is just this j, the current, times d tau prime, then divided by the cursive one, the separation vector between the between the current and also the vector r that we want to calculate the value. Okay, so this is what we have. Okay, so of course this is the equation we do it this for the volume current density. Okay, so if we have the line charge, what we need to do is just to replace this with j with the current. Okay, we integrate over some small element of length. Okay, and divided by the cursive r. So if there is a surface current, okay, so we just replace this j with this surface current density and times dA prime, okay, divided by cursive r. Okay, so that is how we really calculate the vector potential, for different cases. Okay, for the next lecture I will show you some examples how we figure out the